Wet scan. It has become a very relevant tool, and it's something that is very important, especially for this last reason that is here, which is code compliance. Some code will require you, especially ASME, will require you, not only ASME, even the PS ISO standards, they will require you to plot your DAC before you start your scanning. Why do we need to plot the DAC? What is the relevance of the DAC? I listed them here so that it's easy for me to explain them. But before we go into this, let's really look at what is the DAC curve and what is the rationale behind it. Normally, the DAC stands for Distance Amplitude Correction. So your DAC curve now becomes your Distance Amplitude Correction curve. What does this mean? We know that in theory, if I have, say, a thick material and I put a probe there, we know that as the ultrasound goes into this material, the intensity will be reducing as it progresses down. So if I have, say, I have an indication here, I have an indication here, and I have an indication here, because this is closer to the surface, I am likely going to get a much more higher amplitude echo compared to this one and this one. So if this is A, this is B, this is C, I'm expected to have something like this, A, B, C. What it means that as the depth of penetration is increasing, the intensity of the ultrasound is reducing. So which means there is a correlation between the depth of the ultrasound and the intensity. The intensity now of the ultrasonic beam, which is shown now in your UT machine as the height of the echo. So what the DAC curve does is a kind of curve that helps us to plot how the intensity reduces as the depth of the ultrasound, as the depth of the material increases and the intensity of the ultrasound beam reduces. So, which means if I have a thickness that is low, I will have a high intensity, and as the thickness is increasing or the depth is increasing, I will have echoes coming out like this. If I connect these points together, this curve we are getting is what we call the distance amplitude correction curve. Now, what the curve does is it corrects for amplitude changes as the distance of the ultrasonic beam is increasing. So, which means the deeper the ultrasound goes, the lower the echo becomes, and then the lower the intensity, like as I've already said. So if you are able to find a way to plot a curve like this, either physically or electronically, you have obtained your distance amplitude correction curve. The first thing you are going to notice with your distance amplitude correction curve, first thing is this: one is related to your amplitude, just as we said, amplitude. So, and remember when we talk about amplitude, we're talking about your percentage of your full screen height in relation to what we call your dB. But when we plot our DAC curve, we try to keep our dB to be constant. So you keep your dB constant, which means if I have a dB value of, let's say, 20 dB, when I get my first echo, as I'm changing the distance, my dB must remain constant. So what changes now is my percentage full screen height, which is my amplitude representation. So I probably, maybe I'm at 80% initially, and it keeps dropping and dropping until a particular point it becomes so small before I plot my curve. So that is the first thing you're going to notice with the amplitude correction curve. There is a constant dB drop. What does this indicate? Which means if I'm plotting a DAC, those of DAC in the true sense of it will come like this. In the true sense of it, the DAC will come like this. This part of the DAC normally, if you're able to do it, takes care of your dead zone and your near field effect. So, but most of the holes and the distances we are going to use makes our DAC start from this point. But beyond this starting point, if I'm drawing a DAC and I'm seeing something like this, for example, this is not a true reflection of changes in amplitude. So this DAC is probably wrong. Why I'm saying this because it's very important. When you plot your DAC, how your DAC curve comes should tell you if you have plotted it correctly, because you might end up picking the wrong echo. Or I get a DAC that comes like this. Of course, this is also wrong. So your DAC should come as one clean curve with decreasing amplitude that is clearly shown. Now, another thing you're also going to notice when you are plotting your DAC, the dimension of the O, because you are either going to use two kind of O when you are plotting your DAC. You are either going to use a side drill O, or you are going to use a bottom drill O. What do we mean by side drill hole? The side drill hole, as you can see from this, the hole is drilled from the side of the plate, while in the case of a bottom drill, this hole, as you can see in this block, is drilled from the bottom of this block. So this gives you your bottom drill hole, which is at the bottom. The probe is here. In this case, this is your side drill hole, and your probe is here, and the hole is on the side. So you have to keep your holes that you are using to plot your DAC, you have to keep them uniform. So do not start with 1.5 mm and continue with 3 mm. This is going to be wrong. Then, because of advances in technology, we now see that in those days, when you plot your DAC on the machine, you put a screen, you put a sheet or something, a transparent sheet, and you manually plot it. But these days we have electronics that enables the machine to plot the DAC without you manually doing it. So when you start plotting your DAC and you say plot or whatever the machine nomenclature says you should do, the DAC automatically comes out. So that's just the overview of the DAC as a concept. Now, why do we need DAC? If I start from number 6, which sometimes will compel you to draw your DAC, is code compliance. Your procedure may require that you plot and draw a DAC before you start doing the job. You have to comply. So one might ask, is it necessary to draw DAC? I would say not necessarily so. If there is a defect on a plate, you will see the defect. But there are advantages that the DAC curve gives to you that will make your work very easy. If I have a lack of vision in the word, lack of vision is lack of vision. I will easily get it if I know what I am doing. But the DAC will make it easier for me to do my analysis and all that. But if your procedure or your code says you should plot a DAC or you should draw a DAC as it is, you have to do that to comply with the requirements. And most of the flaw detection job you are going to do, you need to plot DAC. If you are doing thickness measurements, you don't require a DAC. But there are some jobs also you will be doing with your 0-degree probe. For example, if I'm scanning a shaft, a very long shaft, I will need to plot a DAC for me to know when I see certain indication within the shaft. Even though it's 0 degree that I'm using, I will be required to plot a DAC. So when you want to do a job, please go through the procedure or the code and see whether you are required to plot a DAC. It is very important. So code compliance. Then the second thing is verification of calibration. When you see somebody doing a UT job and you maybe go close to him and you look at what he's doing and you see that there's a DAC curve drawn on the screen, you obviously know that the person has calibrated properly. He has done the needful, so you can easily know. And also, when you plot a DAC, you are verified also indirectly that the linearity of the unit is okay. that the sensitivity is good, that every other requirement, your range calibration, that they are all correct. So this is just one very easy way to verify that your calibration is correct. Then the next one is your quantitative evaluation of defects. That one we'll look at it more in details when we start looking at wet scan and sizing. But for those of us that have had some experience in doing wet scan, you will discover that by the time you have a defect, you will be told to compare the height of that your defect to your DAC location, to your DAC curve. So at the end of the day, your report sheet, you see where they put DB. Or in some cases, they will say DB to DAC. So at the end of the day, when you are done with your evaluation, you can either put plus 6 dB, minus 6 dB, or whatever the case is. This I will explain some other time. But basically, what this thing tells us is that if I have a defect that has plus 6 dB, it means that the amplitude of the indication is 6 dB higher than the particular point in the DAC curve. That is a topic for another discussion. So with your DAC curve, you can do an evaluation of the height of your defect, whether the defect touches the DAC or not. A very good example, if you have what we call the specular defects like lack of fusion, they usually produce very high echo. The dB evaluation will always be plus. Then if you have indications like porosity that usually have dispersive nature, the scatter UTB, you always get the dB evaluation to be negative. So we use DAC for that evaluation. Then when you plot DAC, you ensure consistency in your sensitivity across a different range of thickness. Earlier on, I was talking about shafts. So if I have a shaft, so this is a long shaft, and I'm trying to find a crack inside with a 0-degree probe. If a crack is somewhere around this area, in your UT screen, we are going to see it as a very small level compared to when the crack is at this point, which we are going to see at a higher echo. What this tells you is that if I'm doing a scan on this shaft and I see a very small amplitude indication, it might just be a defect that we are looking for, but somebody might just ignore it and say, no, that's not a defect, it could be noise or grass. But if you have a DAC that you have plotted and you know that your DAC echo at this point will always be at this height, and you are getting something crossing the DAC, it will obviously tell you that something is actually causing this echo. So because of that, you are able to consistently get echo heights and track them as your thickness is changing. Then also it provides a reference for analysis and for flaw detection. You always hear things like this. If your indication crosses your DAC curve, you should analyze it, you should look at it. But if your DAC does not cross, if your defect does not cross your DAC curve, or it does not cross a certain percentage of your DAC curve, you can ignore it. So DAC provides a very quick reference. That's why we say DAC curve is a reference curve. It's a reference curve. A reference curve that you can use to just do quick acceptance and rejection of any indication we are getting. So it's very good for that, and it also helps in your analysis. Then DAC compensates for beam attenuation. And when you look at this compensation for beam attenuation, that is when you talk about the cousin of the DAC, which is the TCG, the time connected beam. So this basically does what they do the same thing, but with different representation. So you are able to compensate for your dB drop because you have a DAC, which tells you where the height of your echo should be. So we're not talking about TCG today, we are looking at the DAC. And so we'll look at practically how to plot your DAC. So now we'll be looking at how to plot your DAC curve. The first thing you need to have if you want to do your DAC curve, you need to have a block. some people will say you should have a DAC block. There are some blocks that are specifically called DAC block because they are designed specifically for the purpose of DAC. Some other blocks, you can use them for DAC, at the same time you can use them for the other purpose. If you look at this is a typical attachment block. They come at different sizes for different purpose. If you look at this now, you will see this is one O, this is the second O, and this is the third O. Normally for these attachment blocks, you usually have them, you have the holes at so if I have the block and we have O at a quarter of the thickness, I will have another O at half of the thickness, and I will have a third O at 3/4 of the thickness for most of the attachment block. Then you have your popular A5 block and your IOW block, which is this thick block with this one has about 4 holes. You can see these holes here. So this O. So this IOW block, it does DAC and also some other purpose. Now, if you look at this block, this is a specifically designed DAC block just for the purpose of DAC. You can see 1, 2, 3, 4, 5, 6 O's. This has your 1.5 mm drill hole. You can see that the holes are small. You can see this one has a much more bigger hole. So you have your 1.5 mm, you have your 3 mm. The type of hole you are supposed to use, like I said before, it depends on the sensitivity that we are supposed to use. You can check out the video we did on sensitivity. We talked about that. So 1, 2, 3 blocks, they are used for plotting DAC. You can use them for angle probe, and sometimes some people have tried using them for 0 degree, but they are mostly used for angle probe DAC calibration. The best probe for 0 degree, this is not the best probe. You don't use this one for 0 degree, but some people want to use it. But why this may not be so useful is because you have a block and you have a hole here, and then when you put the reflection from this may not be as good as this bottom drill hole, but you can still try it and see how it comes out. But what will guide your choice of block? What will determine the block that you are going to use? Like I always say, go to your procedure, go to your standard. Whatever job you are doing, if the job says you can use your IOW block, use your IOW block. If the job says you should design a specific block, like Asmel would say, pick that specific block. Because sometimes when you are choosing blocks for DAC, you need to consider what we call the thickness of the material. So some procedure will require you to fabricate a block that has thickness that is closer to the thickness of the material you are doing. So for 0 degree probe, we use what we call the bottom drill hole. This is a typical bottom drill hole. The hole is drilled at the bottom. They are usually 2 types. So you have the area amplitude block, and you have the distance amplitude block. What's the difference? The area amplitude block, here you have, normally they are usually 10 numbers with specific dimensions, similar to what we have here. But this may not be the exact dimension as per standard. When you look at the standard, they will give you the right dimension. So you have, for the area amplitude, you have the area changing. What it means is that if this is the O, the size of the O, the depth of the O will be constant. What will be changing will be the diameter. So you have 10 blocks with changing diameter of O, but the height will be constant. So what is changing is the area. In the case of the distance amplitude block, you have the diameter of a hole, which is typically what we have in this block. The diameter of the hole is constant, but what we are changing is the height. So for each block, the height is changing. They are usually 10 numbers. So this will simulate variations in height. So that is the bottom drill hole. So we basically use them when we want to plot DAC for 0-degree probes. So now we look at the steps to plotting the DAC. For us to coherently follow it, I have decided to list it, and then I will just briefly explain them so that I'll get an idea. So the first step before you plot your DAC, you must calibrate your equipment. I've done a couple of videos on this before, you can check them out. Of course, we are going to set up, then you are going to do what we call your range calibration. Then, of course, you are going to set your range. So, you have to do all this so that whatever readings you are getting from your equipment is correct. So, you cannot go straight to plotting DAC without calibrating the equipment. So, you need to do that. Then the second thing to do is to identify the holes you are going to use to plot your DAC. So I have a range of blocks, but I'm going to illustrate with this Asmed block. What I said here, you need to use minimum of 4 holes. So the question is, how many holes do we have on this block? If we count, we have 1, 2, and 3. This block only gives us 3 holes. So how do we get 4 holes from this? Because it's possible to get as many holes as possible that you want to get from this. The idea is just simple understanding of geometry. From the previous explanation I gave to you, I told you the holes. One is 1.4 of the thickness, one is half of the thickness, and one is 3/4 of the thickness. If you look at the way they are arranged on this place. So you can take this as your first O, your second O, your third O. To get the fourth O is easy. You just put your probe and reverse in the direction you started from. The second skip should get this. This becomes your fourth O. If you want to get the fifth O, you put your probe this way, you come back, this becomes your fifth O. If you want to get your sixth O, you put your probe here, you put it hits this. So from these 3 O's, I've been able to get 6 O's by taking the second skip, which is the second leg. So they reflect. So if I want to get first O from this, I put the probe here. And I get this O from here. The second time, if I still want to use the same O, I put it here. It will bounce off this edge and hit this again. So with these 3 holes, I can get as many as possible. But if we are going to plot our DAC, we said use minimum of 4 holes. Why do we need minimum of 4 holes? So that we can get better coverage. You don't want to have a screen that is this wide and you plot a DAC that ends somewhere here. You will be limited in the distance you are covering, and if you have indications that are coming out at this point, you will not be able to assume. But if you plot your DAC with a lot more points, your curve is going to go and cover a lot of it and cover your screen properly. That's why we encourage minimum of 4. You can do more than that. The next thing you are going to do is to turn on your DAC. This part is very, very important because some people get themselves into trouble here. So ensure that before you turn on your DAC, you've done everything you need to do in terms of setup and calibration. Because immediately you turn on your DAC, your velocity and every other thing related to your pulsar and your receiver, they will be frozen. It is just a safety measure that the manufacturers and the designers of the equipment have done so that you don't start changing figures when you start plotting your DAC. That's why we said you don't need to alter your dB, you don't need to alter anything. The only two things that will change once you have turned on your DAC is just your gate and your dB. And these are the only two things you should adjust when you start plotting your DAC. Do not go touching velocity, do not go touching. You can't do any other thing because it will be frozen. And so ensure that you have done everything you need to do before you turn on your DAC. So you are left with only adjusting gates and dB. The other button you are going to adjust is your set. If you are using an equipment like your Olympus, if I'm using this Olympus, your set button will always be there. It's just for you to click to plot. To set means you are accepting the point. If you are using a unit like your solar test, you press on this OK button for some seconds and it accepts the points. So you just need to do that. This usually gives a lot of technician problem because they are wondering where is the plot button. Just press this on. If you are collected your point, press this for 5 seconds and it will accept. So you're only going to be able to adjust your gate, your dB, and your set button once you turn on your DC. So you need to ensure you do what you need to do. Then the next thing you are going to do is to select your DAC type. This is usually very important because a lot of people still don't understand what to do when you get to this point. So what do you do? Normal, standard, single, depend on the nomenclature your machine is using. It means you are just plotting one DAC curve. One curve is going to come out. In the case of ASME, your ASME block, or your ASME DAC rather, you are in normal typical ASME, you are going to get a curve that is just one, but it's in the ASME format. It follows the ASME rule. In the case of ASME 3, which I will explain now, ASME 3 means as you are plotting, you are getting 3 curves, not just one, you are going to get 3 DAC curves. 3 DAC curve while you are plotting. Why some equipment, I think solar test does that, even Olympus, they can allow you to start by plotting your standard or your normal curve. After plotting, it gives you the option of splitting that one curve into an asymmetric curve. So what is the meaning of this asymmetric curve? Because most of the tests you are going to be using, you are going to do them with the asymmetric curve. This is advisable. How does it work? So this is what happens. When I plot my initial DAC curve from, as you can see below, we will plot it to what we call the 80% full screen height. So which means the echo gets to 80% and we set this point. We go to the next one. The assumption is that this 80% full screen height is controlling the other ones. So that gives us one curve. One curve. This is 80%. How about if I want 40%? I want a curve that is representative of 40%. So, which means here we're supposed to be 40, here will be 40, here will be 40, here will be 40. And 80 to 40 is minus 6 dB. Then I can say, you know what, give me 20 also, which is minus 12 dB. So if you look at an equipment like solar test, it gives you the option to choose minus 6 dB or minus 12 dB. So you will see this option in the machine when you are making selection. So how does it become asymmetric? You have this one which is at 80%, you have this one which is at 40%, you have this one which is at 20%. So you have your dB and 2 extra. That makes it 3 curves. It can also give you minus 14 dB, minus 12, minus 20 dB. It can give you a lot of options, but at the end of the day, you will be getting an asymmetric curve. So other machine, if you just select asymmetric curve, three curves will just start plotting instantly, immediately you start plotting. While some other cases, you just plot one curve and split it into three. That gives you what to call your asymmetric curve. The next option that is available to you is the JIS, the Japanese Industrial Standard. This is really used on this side of the world. In Asia, they use this, but this way we don't select this. So you can experiment on your own and see what comes out of it, but I'm not going to be talking about it here. So, what will I advise? If your machine can start with your normal curve or your standard curve, draw your standard curve. When you are done, split it to an asymmetric curve. Or if you like, you can start with an asymmetric curve and you complete whatever you are doing. But just pick the option that is good for you. If you are using a unit like Sonar Test, you can start with your standard or your normal curve. When you are done, just go to options. Your machine gives you the options to select your asymmetric. The next thing you are going to do now, say using your first O, which is the smallest distance. If we look at this one, from what we've said, from this block, we are going to use 1/4. 1/4 of the thickness. So, which is this O. So, we are going to start with this. So, you set your probe, you identify this probe you set, and you will obtain an echo. We'll practicalize it shortly. Then, when you get an echo in your machine. Say this is your screen. You get an echo. This echo, you maximize the echo. What do we mean when we say maximize? Because you keep hearing this term maximize. It means keep moving the probe back and forth until you get the maximum echo you can obtain. So play around it back and forth until you get the maximum echo you can get and stay at that point. That is the echo that you will need. So you maximize the echo, and after maximizing, what do? You set the echo to be 80%. So let's say I maximize and I get an echo that is somewhere around 40% of the screen. What do I need to do? I go to the dB button. I start adjusting the dB button. In this case, I will be increasing the dB until the echo gets to 80%. If the initial echo I got is so high and is above 100% of the screen, I go to the dB. I start reducing the dB until it also gets to 80%. Immediately it gets to 80%, what do? We say this is your reference dB. Do not change it. Do not change this dB. So let's say I adjust the dB and I get 52 as my dB value or as my gain value. This gain value, do not touch it after using the first O. Do not change it until you finish plotting your dB. As a matter of fact, we encourage people to write this down. Note this down somewhere in case you mistakenly go and adjust your dB. You always know this is called your reference dB. If it's available in all modern machines. You can go to the machine and set this value as your reference dB. Or in some cases, immediately you plot your first point, the machine will automatically grab that value of this dB and it will set it as your reference dB. So do not change it. The next thing you are going to do with this echo at 80%, hold your probe firmly and adjust your gates. Now, in some units, typically your gate is usually something like this that you can adjust up and down. So if I have an echo at this point, and I want to get this, I start adjusting my gate until my gate gets to this point. But when you are putting your DAC, you are not going to get this kind of gate. The kind of gate you are going to get is a band like this. A dark band like this. Unlike your normal gates, you don't have to do, the only thing you can adjust the width of this band. So what you need to do, you move the band until the band is crossing this dB. Immediately start crossing this echo, you just go to your machine and you say set or asset. Depending on the UT equipment you are using, just click asset. It is going to put a dot there. it shows that it has taken that point. Some machine will say go to the next point. So what do you need to do? You already have your first point. You go to the next hole. Or in this case now, we'll go to the hole that is after the which is this. Now, we have set, immediately we have set this first point, we have set our reference DB. We are not changing DB again. The only activity we need to do now is to repeat the process. We put this, we maximize until we get the best echo that we can get, the maximum echo we can get. We go to our gate, we adjust this gate to this point again, and do what? We are setting it again. Until you do that. When you have done that, if it is 4 holes, you do it for your 4 holes. I've told you if you want to get to the 4th hole for this, you know what to do. You flip the block and you take it at the second step. When you have done all that, some machine will tell you to draw, or some machine will tell you to finish, or some machine will say, whatever the term they use. I have always encouraged, let me reiterate it, read your equipment manual. It is very important. They will clearly tell you what you need to do. Even in plotting DAC, they will explain the concept for you in the manual, how to do the DAC using that particular equipment. The manual will not come and explain what the DAC does or how to maximize and all that, but they will tell you the steps to take to plot your DAC. So you just follow and plot. When you are finished, you just say draw, finish, and automatically the curve will come out. That is in some machine. In some others, as you are adding the point, your curve will be coming. As you add the second point, your curve will come out. As you add the third point, your curve will continue like that until you finish. In some other cases, you will not see the curve until you are done plotting. So watch out for what your equipment gives to you and follow. If you follow this process at the end of the day, depending on the setting you choose, if you choose to get one curve, you just get your standard one curve. Then you can now go to option and turn on your asymmetry, depending on how it comes. If it is for Olympus, it will just give you asymmetry. You just see asymmetry, 3 curves will come out, which are 80%, 40%, and 20%. That is minus 6 dB, minus 12 dB. In the case of sonar test, it will just give you option of minus 12 or minus 10, minus 14, depending on the options that are available for you. Then you'll see 3 curves that will come out. So that way you now have your DAC. How you go about using the DAC is a subject for another video.